This is the example that we left off on last week, and I'm going to modify this because this just takes an awful long time. Let's do Krypton because he reminds me of Superman. So, to prevent the presence of air, noble gases are placed over highly reactive chemicals to act as inert blanketing gases. So these are chemicals that even if you sealed them up in a container, just the air in the container would react with them. And so this is one technique for keeping the air away. Another one is to put like oil on them, so they'd be like swimming in oil. Chemical engineer places a mixture of noble gases consisting of 5.5 grams of helium, 15 grams of neon, and 35 grams of krypton in a piston cylinder assembly at STP. Calculate the partial pressure of krypton. We're going to not do all of them because it's tedious and repetitive. Okay, I read the question. We've got some masses. And we also have at STP. What is STP? Standard temperature and pressure. So that's telling me what the temperature and the pressure of this gas is. And then we're trying to calculate the partial pressure of krypton. So this is going to make use of an equation. This is not one we can do with unit conversions. So we learned that the partial pressure of a gas in a mixture, so here krypton, is going to be equal to the mole fraction of that gas times the total pressure. At STP tells me that the temperature is 0 degrees Celsius or 273 Kelvin, and that the pressure is equal to 1 atmosphere. And those will be considered exact in calculations. So this is my P total. That is the total pressure of all those gases together. We're trying to find the partial pressure of krypton, and so what that means is I need the mole fraction of krypton. So mole fraction of krypton would be the moles of krypton divided by the total number of moles of everything. If it was a percent, then we'd multiply by 100. So like a percent, it's the part divided by the whole. So we're looking at moles of krypton divided by the total number of moles, which will be moles of helium plus moles of neon plus moles of krypton. And that's equal to the mole fraction. So we were given masses. Can we convert those to moles? Yeah. So 5.5 grams of helium. Use dimensional analysis here. I want to divide by grams and multiply by moles so that the units work out. That way I don't have to remember, should I divide by the molar mass or multiply? The units are just going to show me what to do. We look at the periodic table. We see that 1 mole of helium weighs 4.003 grams. And so this is 1.37. Now, good enough. So this is where it's just a little tedious, is we have to do this 3 times, right? So then we've got 15 grams of neon Oops. And neon was 20.18. So I want grams down here, so the grams cancel, moles up there. 1 mole, 20.18. Yeah, short-term memory problems. So 15 divided by 20.18. That's going to be 0.74331 moles. And then the last one is the krypton, 35 grams of krypton. And again, dividing by grams and multiplying by moles in krypton, 83.80. So I've got moles of helium, I've got moles of neon, and I've got moles of krypton. So the mole fraction is going to be, the moles of krypton divided by the total number of moles. So the total number of moles, I'm just going to take those numbers and add them together. Two point 5349 moles in total. This is an example of where we have some multiplication. So we're starting with masses with 3 sig figs. We're multiplying, we end up with 3 sig figs. Now we're taking these and adding them. This one has 2 decimal places, these have 3. So this total is going to have 2 decimal places. If you're interested in those sorts of things. What happens to the units? They cancel. A mole fraction doesn't have a unit. It's just a number between 0 and 1. So this is my mole fraction. That's what I'm going to plug in up there. Let's do a different color here. So the pressure, partial pressure of krypton is going to equal 0.16476 times the total pressure, which is 0.164 atmospheres. And then in the original problem, you repeat this part and this part 2 more times. Ugh. Any questions?
One question on moles.
You take the moles of all of them and you divide it?
Right. I want to find the mole fraction because the pressure of a gas depends on the number of moles, right? And so this mole fraction, basically this is saying that 16.5, yeah, I rounded that wrong, because it looked like a 2 down here. That's a 7, isn't it? Okay, this is supposed to be a 5. 16.5% by moles is krypton. So then krypton is going to exert 16.5% of the pressure.
Okay.
And this is just calculating a percent without multiplying by 100, because then later we'd have to divide by 100. So it's the moles of the part we're interested in divided by all the moles.
And the bottom part, what is that? The bottom 2.5349?
This is the total number of moles. So I calculated the moles of each gas, and then I added them together. And I did the bracket because I didn't feel like writing them down again. Any other questions? No?
I had forgot.
A gas mixture contains an equal number of moles of helium and neon. The total pressure of the mixture is 3.0 atmospheres. What are the partial pressures of helium and neon?
Oh, I have a question now.
Okay,
What question is this on the worksheet? It's not the same question, but like,
I don't know the numbers of the worksheet questions off the top of my head.
I just wanted to work it out while you were.
Yeah, sorry, you'll have to look through it and find it yourself. So if we have equal moles of these gases, what does that tell us about their pressures? What'd you say?
I don't think that's right.
I heard something, but I couldn't understand it. So we just saw that the partial pressure of a gas is equal to its mole fraction times the total pressure. If the mole fraction, well, if the number of moles are the same, then the mole fraction is going to be the same. So will the partial pressures be the same? Yes, they will. So from that first sentence, we can see, well, the partial pressures must be equal because it's 50%, 50% helium and neon, so they're each contributing half of the pressure. And the total mixture, total pressure is 3, which tells me that the sum of those pressures has to be 3. So which one is the answer? C. Any questions? Yeah.
What was the formula again? You said partial pressure times the total pressure?
Yes. Let's find that. That is this guy down here. So the partial pressure of a gas is equal to its mole fraction times the total pressure. I'm going to skip that one because there's another one almost exactly like it coming up. So we started the chapter talking about breathing, and we talked about pressure under the water. So when a diver goes deep under the water, they have to breathe compressed air. And so that's going to have a higher pressure, of course, but that means the partial pressure of oxygen is also going to be higher. And we might say, well, oxygen is a good thing, right? Yeah, but too much of anything will kill you, right? So if you're breathing air with a partial pressure of oxygen that is too high, that can harm you. It's called oxygen toxicity. And that's going to happen when you get up here around 1.4, 1.5 atmospheres. You get too much oxygen in your tissues. Of course, the other extreme isn't good either. Not enough oxygen. This is called hypoxia. Hypo, like below. Oxygen is too little oxygen. So that's going to also cause a problem. Well, air is about 78% nitrogen and 21% oxygen. So if you're breathing compressed air, you're also going to have a higher than normal partial pressure of nitrogen. And that can cause something called nitrogen narcosis or rapture of the deep. So the symptoms of that are similar to being drunk with alcohol. And this is, very dangerous deep down under the water because you need to have clear judgment and be making good decisions when you're scuba diving. Or deep sea diving in particular. So what they do to get around this is they breathe things other than air. One mixture that is used is called Heliox. It's a mixture of helium and oxygen. So you need the oxygen to live. The helium, all that does is give you a squeaky voice, which nobody can hear down there anyway, but it doesn't get into your tissues and cause problems like nitrogen can. So up here at the surface, with a total pressure of 1 atmosphere, we're going to have 0.78 atmospheres of nitrogen and 0.21 of oxygen. Down here at 30 meters, now we've got, in order to be able to breathe, we have to have a pressure of 4 atmospheres. And so the partial pressure of nitrogen is going to be 3.12 atmospheres, and this is getting close to where you're going to have nitrogen narcosis. Any questions about that? So a diver breathes a Heliox mixture with an oxygen mole fraction of 0.050. What must the total pressure be for the partial pressure of oxygen to be 0.21 atmospheres? So I'm given this and this, and the question is partial pressure of oxygen. Well, oxygen mole fraction, that would be that funny X, O2, 0.050. No units on that. And partial pressure of oxygen would be P, O2, and that's 0.21 atmospheres is what we want. And why didn't you guys stop me? Just want to see me implode? This isn't the question. We want the total pressure. So we're trying to find the total pressure. Well, there's an equation for this one. It's the same one we used in the previous example. The partial pressure of oxygen is equal to the mole fraction of oxygen times the total pressure. So here we want to rearrange this equation to get the total pressure by itself. So the total pressure will equal the partial pressure of oxygen divided by the mole fraction of oxygen. So partial pressure is 0.21 atmospheres divided by 0.050. 4.2 atmospheres. Any questions?
The mole fraction is something divided by something, and that's what it equals? It's not like that's what goes in the mole fraction?
So here they're telling us the value of the mole fraction. Yeah. So they've already calculated that for us. Yeah. When we have a chemical reaction that generates a gas and we want to collect the gas, maybe to see how much there is, an old-fashioned and very straightforward way to do this is by collecting the gas over water. So the way this works is you take a beaker or some other container and you completely fill it with water and you invert it in a dish of water. So this is a lot like a barometer, except it's water instead of mercury. Here we have our reaction occurring in this test tube, and we're allowing the gas to escape through a tube, and we're directing it so it has to come up under this overturned beaker. As the gas is formed and goes up, it's going to displace the water. So all the hydrogen generated here is going to end up over here, but then this is not going to be pure hydrogen because there's water and the water will be evaporating. So we're going to have a partial pressure of water and a partial pressure of hydrogen. We call the partial pressure of water vapor the vapor pressure. And it depends only on the temperature. So if you measure the temperature of this experiment, you can just look up the vapor pressure of water. And then you would subtract the vapor pressure of water from your total pressure to get the pressure of the gas that you are interested in. So this is the question that was similar to the previous one. A sample of acetylene is collected over water. The total gas pressure is 738 torr and the volume is 523 milliliters. At the temperature of the gas, the vapor pressure of water is 21 torr. How many grams of acetylene are collected? This is one of those problems with so many words. Well, let's focus on the numbers and the question. So I have a pressure here, 738 torr. I can identify that because it says the total pressure is. Also, I can look at the unit. The volume is 523 milliliters. And the vapor pressure of water, which would be the partial pressure of H2O, is 21 torr. And I missed the temperature. He'll go in here. 23 degrees Celsius. An important thing here to not overlook are those three words, collected over water. In this example, they're telling us what the vapor pressure of the water is, but on some problems they won't mention the vapor pressure of water. So when you see collected over water, that means you need to subtract the vapor pressure of water from the total. So to calculate the grams of acetylene, we're first going to calculate the moles of acetylene using the ideal gas law. And the total pressure is equal to the partial pressure of acetylene plus the partial pressure of H2O. So that means that the partial pressure of acetylene, which is what we're interested in, is equal to the total pressure minus the pressure of the water. .717 torr. So we're going to use the ideal gas law to calculate, I'm going to start it way up here, the number of moles of acetylene. So that's going to equal PV over RT. Are any of our units the correct units? No, they're all messed up. What do we need instead of torr for the pressure? this needs to be in atmospheres, because that's the unit of pressure in the ideal gas constant. Remember-
Is MHG a unit as well?
Yes, millimeters of mercury and torr are exactly the same. Yeah. So then the conversion factor is also the same. So 717 divided by 760, 0.94342 atmospheres. And the volume, well, we can fix that by saying 523 times 10 to the minus 3 liters. And then for the temperature, we need to convert to Kelvin. So we've got 296 Kelvin.
And for these problems, we don't just use 21 torr, because they told us the vapor pressure for water.
Yeah, they told us the vapor pressure of the water, but we're trying to find the information about the other gas. Yeah. We didn't want the water in there, but if you collect a gas over water, there will be water in there. Okay, so I can plug these numbers into my equation up here. 0.94342 ATM, and my volume was 523 times 10 to the minus 3rd liters. Dividing that by the ideal gas constant. And the temperature. Now, do this on your calculator to make sure that you are on the same page with your calculator. Because there are a lot of disagreements that happen when we do a calculation like this. If you get 1,779, you have a disagreement with your calculator. We are dividing by numbers that are multiplied, so most students find it best to use parentheses here, times sign there, another parenthesis over there. Everybody coming up with the correct number? So to convert moles of acetylene to grams, we need the molar mass of acetylene. The formula was given there, so 2 times 12.01 plus 2 times 1.008. So I'm going to take the moles that I just calculated. I'm going to look at the units. I want grams, so I'm going to divide by moles. The number goes with gram. And 0.5288. So 0.529 grams of acetylene is collected. Any questions? Calculating the moles of a gas or the mass of a gas collected over water is like just a favorite problem of most chemists. So it's gonna come back. You'll see it probably on the exam. Any questions? And there's another one. I don't see the point in doing another one. Why are there 3 of them in here? Anyway,